This segment covers steering data wavefronts to the background of null emptiness. When we steer a data wavefront, we steer it to path A or to path B or to path C, and those paths become OR related. And if the wavefronts are freely flowing through those paths, then when they try to converge, there can be a race. We'll cover that race, we'll cover how to manage that race, and we'll end up with a prototype of an ALU circuit. We will implement the steering with the steer column component. Each column is a variable. In this case it's 4 bits, in the example it's 32 bits. So this is column for A, the column for S, and the column for T, and we'll steer A to either S or to T based on the steer variable. And the steer variable, this rail of the steer variable, will enable S, which will enable A to flow to S, or it will enable T, which will enable A to flow to T. So we'll begin with full word completeness, and here we're taking the completeness of each digit and then the completeness of all the digits to get the full word completeness. And we'll get a completeness for either T or for S. So the completeness for the component is either this or this. So and that will close with A, and that will close with steer. So we'll build the column by stacking up digit slice components. Right, so we have a component, the steer f.v, which will steer A, bit 1 of A to bit 1 of S, or to bit 1 of T, and then we'll do one for 0, and we'll stack up 32 of these to get our steer column for our examples. So next we take the steer variable and we pipeline it down the columns to get 2D pipelining, right? So the steer variable will steer bit 0, and then it will pipe along and steer bit 1, and then pipe along and steer bit 2, and it has its own pipeline, orthogonal pipeline to the data flow. And then we get 2D pipelining. So next we optimize the 2D pipeline steering. The first observation we make is that any completeness here means that that digit was steered, it was enabled, right? So we can take this completeness to generate the steer for the next digit, and then we can take that completeness to generate the steer for the next digit. So what's going on here is we're merging the steer pipeline into the digit pipeline, right? If we take this gate and merge it into this link, and this gate and merge it into this link, we're essentially merging the steer flow links into the digit flow links. And if we look, we get the completeness here, and we have this is the OR, right? This is either S or T, and this closes with the steer and with A, right? So now this is the link for the steer, and the steer oscillation now looks like this. Right? It goes through here, and this links this steer oscillation and this steer oscillation. It also links this digit flow and the digit flow through A. So now this is linking 4 oscillations. With the merged links, you'll notice that this gate is now doing completeness for A as well as for steer. In the previous circuit, this gate did closure for A, and this gate did closure for the steer. So now this one gate is doing the same job as both of these gates. So a whole lot has been merged here. There's a lot fewer gates and a lot fewer transitions. So this is the steering column that we'll use for the rest of the examples. This is what the examples look like from the top down. Each one of these is a column, a 32-bit column. This is the S column, T column, U column, V column, A column, and so forth. And A is steered through one of the flow paths, which goes through a buffer, and then the paths converge into a single flow, which goes to the test bench. Our first example just uses a four-state sequencer 0, 1, 2, 3, and it uses the steer component. Our second example substitutes bitriquat, which gives us a little more interesting steering pattern. It still uses steer A. And our third example uses the steer C steering component, which is the optimized 2D flow. So this is the full word completeness flow. We'll look at the flows in terms of the completeness of each digit for each column. So this is the completeness for the digits of the S column, and this is the flow steered through S. So we'll put the timeline marker right on the edge of S, and then we'll look at the flow steered through T, the flow steered through U, the flow steered through V, and then the flow interleaved through the convergence component. So that's the full word completeness. So now we do the 2D steered, and we'll drive the 2D steered with a sequencer 0, 1, 2, 3, 0, 1, 2, 3. Okay, so we're flowing through S. This is S again. And then we'll flow through T, and then we'll flow through U, and then we'll flow through V. And again, this is the interleaved flows through the convergence component. So next we're going to control the steering with the bitriquat output. And if you remember, the bitriquat output went 1, 0, 2, 2, 1, 1, 3. So it's a little more interesting steering pattern. So this is S again, and this is the steering. We'll just put this here so we can get an orientation. And then this is T, right? So this T is 2, so this is 2, 2, and the U is 1, 1, and the V comp is 3. It was backwards. T was 1, 1, U was 2, 2, and the V comp is 3. But anyway, we have a little more interesting pattern of steering here. And again, this is the steered flows interleaved through the convergence component. And the final example is the C. We use the steer C component, and you can see that it does the same thing, 2, 2, 2, 2, 1, and this is the interleave steers through the merge component, through the convergence component. D1, D2, and D3 place adders in the OR-related paths resulting from the steering. A logical analysis would have told us that we have free-flowing OR-related paths and that the OR-related paths converge without coordination, and in that convergence there's a race. Now the digital simulation so far has masked that race from us, and we've taken advantage of that in the previous examples, but now we're going to expose that race by adding a delay in V out in the E simulation. The first manifestation of the race is the failure of the test bench. So here we're going to execute D1, and we see that D1 passes the test bench. And then we're going to execute E, and we'll see that E starts failing the test bench. So this is the exercise with the identical adder added to each of the flow paths. And again, this is the flow through S, the flow through T, the flow through U, and the flow through V, and the interleave flow through the convergence. Now we've gotten by with this interleave flow so far because all four paths have always been logically identical, and the digital simulation turned that logical sameness into timing sameness, right? They have identical timing. So they just kind of lined up through the convergence. But there is really a race in the convergence, and we'll expose that race by adding a delay to one of the paths. We'll add a delay to V. This is the simulation with the race. This is the S flow. This is the T flow, and this looks like what we're used to seeing, but this looks kind of puny. Now this is the U flow, and the U flow has some strange variability in it that doesn't look quite right. This is the V flow, which has the delay in it, and this is the merged flow. And we can see the V flow, the delayed flow, in the merged flow, but we can also see anomalies, right? So here is a situation where there should have been two transitions here, but there's only one. This is sort of like an unglitch, you might call it. But anyway, it's an anomaly in the signal that is fairly obvious. So this is what signals look like with races. We've already seen the race manifested as a failure of the test bench. The other manifestation of a race is lockup. The circuit just quits running. NCL circuits have to be fully logically determined. And a race is a gap in the logical determination. And these gaps can be detected by logical analysis of the specification of the circuit. And once detected, the gaps can be filled in by adding the appropriate logic. So in this case, the appropriate logic is to coordinate the flow into the convergence in the same order that it was steered into the OR-related flow paths. We do that coordination with a select column that enables each OR-related flow into the convergence in the same order that it was steered into the OR-related flow paths. And we do that with the same variable that did the steering. So the steer variable comes in, it steers into the OR-related flow paths, and then we pipe that along to the select column, and then that same variable selects in the same order the wavefronts and the flow paths to flow into the convergence. And the completeness of the convergence regulates this so that only one enable flows at a time. When that's complete, the next enable can flow, and when that's complete, the next enable can flow. And in this way, the independent flows of the freely flowing OR paths are regulated, are coordinated into the convergence without the race. So these are the simulations with the select column, and this is simulation F with select column A. This is the S flow, the T flow, the U flow, the V flow, and this is the merged flow. And you can see the delayed V flow. Everything else looks very regular and very nice. This is the FC simulation with the select C column, and you can see this is the U, and we're passing the V, and now this is the converged, and you can see the V delayed flow, and the rest of the flow looks very nice and regular. And this is the FN flow, and this is with the select A and the delay removed. And this is the T, we're passing U and V, and now this is the merged flow, and you see there's no delay and it's all very regular. All three simulations also pass the test bench. The other way to manage wavefront flow through OR-related flow paths is to not let them flow independently to begin with. This is to treat the wavefront flow across the paths as a single wavefront, single coherent wavefront with a spanning completeness and a spanning enable. And this way, each individual wavefront in the paths is separated by a null wavefront. So the individual wavefronts arrive at the convergence and are enabled into the convergence one at a time in turn. These are the G simulations for the coherent wavefront flow. This is the one with the delay. This is the S flow, the T flow, the U flow, the V flow, and this is the composite flow. And you can see the delay, the V delay, and the composite flow. This is the flow without the delay, and this is the S flow, the T flow, the U flow, the V flow, and the composite flow without the delay. Both simulations also pass the test bench. In our last simulation, K, we put 3 different adders in 3 different flow paths to demonstrate a multifunction component. In K2, we put a forward completeness in the V path to additionally exercise the logical determination. And in K3, we use select C as the select stack instead of select A. This is the converged flow for simulation K with the 3 different adders. We'll spread it out a little bit so that you can see the data variability of the individual flows. This is the converged flow for K2, and this is the forward completeness with each V. Each time V comes along, we get a forward completeness. And then the flows skew again after the forward completeness, and then they straighten up again. This is the K3 simulation with select C stack. And since the select and the data are both going through the same link, the weights and the transitions line up a little bit differently.